Hi folks, this is Nat. This is going to be a video lesson on unit rates. First we're going to go through the different things that go into unit rates, talk a little bit about ratios, and then we're going to talk about how we can set information up into a proportion to solve any problem with a unit rate. One of the things that's going to be really helpful to understand as we start to talk about unit rates is the idea of a ratio. A ratio is like a fraction, except it's used to compare two types of numbers that are measured in different units. Let me give you an example. Let's say I'm driving down the highway, and over the course of 4 miles, I see 8 buffalo. Well, I could express this idea in a ratio. Again, a ratio is a way of comparing things that aren't measured the same way. I can't measure miles and buffalo in the same units. I can't add them together. I can't subtract one from another because they're not the same as each other. But I can express them as, for example, 8 buffalo for 4 miles. And I can write it as a fraction. You'll also see ratios written occasionally, actually really frequently, like this, with a little colon between them. Really common way to write them, but it actually doesn't help us today. We're going to be focusing in on the fraction version. So, if I saw 8 buffaloes in 4 miles, that's a ratio, comparing the number of buffaloes to the number of miles. It's a comparison statistic. If I reduce this fraction down to so that one of the units has a value of 1, then I've created a unit rate. So let's say, for example, I divide both the top and the bottom of this fraction by 4. Then I've created a new fraction, which is 2 over 1. These fractions are equal to each other. The one on the left here, though, like we said before, is a ratio. The one on the right, 2 over 1, is going to be an example of a rate or a unit rate. Anytime you have a ratio and you reduce one of the two sides down to a value of 1, you've created a unit rate, which is a statistic that compares things in terms of values of 1. So originally, when I'm thinking about my buffaloes on the road, I saw 8 buffaloes over 4 miles. When I reduce that, I could say, well, then I saw 2 buffaloes every mile, and that's a unit rate. And I might say that that's the unit rate, 2 buffaloes per mile. You might also notice, and it's important, that when I set this up, or when I look at this, the same unit is in the same place in my various fractions. So the top here always represents buffaloes, 8 buffaloes in my original ratio, 2 buffaloes on top in my unit rate. On the bottom I've got 4 miles, and on the bottom I have 1 mile. So when I am making ratios and unit rates or setting up a proportion for these things, I want to make sure the same unit is in the same place in the fraction, either in the numerator or the denominator. The other thing we want to notice is that when I look at this statistic that I came up with at the end, my unit rate, 2 buffaloes per mile, it's important to see that that is 2 buffaloes per every 1 mile. When we say a unit rate like that, we don't say the 1, but it's really, really important that we recognize that it's there. Because sometimes we'll have a unit rate and we'll want to turn it in, we'll want to use it to find other information. Because unit rates can be really, really useful for helping us solve problems, but we do have to recognize that it's always out of 1. So in this case, if you say 2 buffaloes per mile, that's 2 buffaloes for 1 mile. If I said 8 cookies per student, that's 8 cookies per 1 student. Let's use the same example but change it up a little bit. Let's say I was driving and I saw this time 5 buffaloes in 3 miles. Well, the ratio is still the same idea. If I'm setting that up, I can say, well, I saw 5 buffaloes in 3 miles, and that's going to be my fraction. Again, our ratio can be expressed like a fraction. 5 buffaloes in 3 miles, and those go together. Now, the problem is that reducing these is trickier because I don't have a number I can divide both 5 and 3 by, and neither of those is going to be 1. Or at least they won't be whole numbers together if I do divide them by the same number. That's okay. One thing we want to understand is how we can put this information into a proportion and make it easier to solve possibly. So if I still want to know the number of buffaloes per mile, I can again set this up as a proportion to represent the idea I'm looking for. I know that when I say buffaloes per mile, I'm talking about buffaloes per 1 mile. So we are always thinking about units of 1 when we want to find a unit rate. So miles, I started with 3, but I'd like that to be 1. So I can go ahead and put that 1 in, and then I'm going to say that I know that this is going to be an equal fraction, but the question is, what is going to be that value for buffaloes? How many buffaloes will it be per 1 mile? Hopefully this looks really familiar. We can set this up as a proportion anytime we want. There are other ways to do it, but a proportion is a nice way to represent the idea of reducing it to 1. And if I do this, I can cross multiply and say, okay, well, that must be 3x. 5 times 1 is 5. Lots of multiplying by 1 in unit rate proportions, which is great. And then I can divide both sides by 3 and find out that, okay, the number of buffaloes per mile is 5 divided by 3, which is going to be 1 and 66 hundredths repeating forever. So my unit rate in that situation, and I'll just round it, is 1 and 7/10 buffaloes per 1 mile. So here's another example. Bill has 48 Skittles and wants to give 3 Skittles per person to each of his friends. How many friends can he share with? If I want to think about this, the very first thing that I would like you to start noticing is this idea of the unit rate phrase, which is always the same, something per something. You'll see other words that indicate unit rates. Actually, each here is one of them. Each is a, 1. When each person gets something, one person, each of the 1 people get something. But this idea of something per something, in this case Skittles per person, is a really good thing to start to notice because that's a specific unit rate phrase. So when I say 3 Skittles per person, I'm saying 3 Skittles per every 1 person. So if I'm trying to set up a proportion to solve this equation, I can do that pretty easily because I can already see, well, it's 3 Skittles per 1 person. That's a unit rate because it's out of 1. And that can be the beginning of a proportion. So in this case, we're not looking for the unit rate. We have the unit rate, and we're going to fill in the rest of this equation to help us figure out the answer to the problem. So 3 Skittles per 1 person or friend. Okay, so if I look up here at the top, it says that Bill has 48 Skittles. Well, that's, again, a Skittles idea. Skittles was on top of my proportion, so I'm going to put that on top of my proportion on the other side to match. 48 Skittles, 3 Skittles. Always important to put the same units in the same place. And the question here is how many friends can he share with? So we're going to be finding out how many friends this equates to. If you have 3 Skittles for 1 person, how many can you give to 48? Or how many friends can that be for 48 Skittles? So friends is unknown in this equation, so I might just do F. Once I've set that up, again, I can go ahead and cross multiply and discover, hopefully pretty quickly, that the number of friends I can share with is going to be 16. So there's an example of unit rates being used to find an answer to something else. We're not looking for the unit rate, we're using the unit rate to figure out something else. So here in example 2, we've got Will's car drove 852 miles on 6 gallons of gas. How many miles would it drive on just 1 gallon of gas? So let's start by identifying here what information we have and what information we don't have. Will's car drove 852 miles on 6 gallons of gas. This information all goes together. And this collectively is going to be a ratio. 852 miles goes with 6 gallons of gas. And so when I ask the question, how many miles would it drive on just 1 gallon of gas, I could just recognize that, okay, I'm being asked for a unit rate here in terms of gas. It's going to be 1 gallon of gas. So gas was 6 for 852 miles. Gas is going to be 1 for some unknown number of miles. And I can go ahead and cross-multiply and solve that equation. Really nice to recognize that when you are asked, well, what about if it was just 1, you're basically always in this scenario being asked for a unit rate, because a unit rate is out of 1. And if we go ahead and cross-multiply, we'll say that 6x is equal to 852, and we'll divide both sides by 6. So in this case, on 1 gallon of gas, you could go 142 miles. So the unit rate we could describe here is 142 miles per gallon, or 142 miles per 1 gallon. Last example, Elizabeth ate cookies for 12 minutes at a rate of 3.5 cookies per minute. How many do you think she ate? Again, ideally what might jump out at you, similarly to working with a percentage equation, where the percent hopefully jumped out at you and you said, oh, that's helpful, I can set up a proportion this way, is this phrase here, cookies per minute. So if she's eating 3.5 cookies per minute, that's 3.5 cookies in 1 minute. And we can start off our equation this way, 3.5 cookies in 1 minute. The other side of the equation is going to be based off the other information we have. Elizabeth ate cookies for 12 minutes. So here I've got a little more information. She's eating for 12 minutes. In my unit rate, minutes is on the bottom. It's a 1 minute chunk, 3.5 cookies in 1 minute. So when I set up the other side of the equation, I'll match that. I'll have minutes on the bottom, so 12 will be on the bottom. And then what's missing is how many cookies she ate in 12 minutes. So that's our variable. So cookies was on the top, and that's where our variable belongs. So pretty quick to set these up, as long as you match the types of units to each other. I'll go ahead and cross-multiply and solve. So 3.5 times 12 is going to be 42. And x times 1 is just x, so I don't even have any next step here. I just know that the value of x is 42. So that must mean that she ate 42 cookies in 12 minutes. Hopefully at this point you're kind of beginning to understand the idea of unit rates. Go ahead and give these practice problems a shot. Good luck.